Okay, so welcome to the second video. In this video, we will discuss the orientation issue, but with a slightly different explanation. Okay, so now let's take these examples here with with electron with electron uh, donating a group. Okay, so to start with, our molecule here is the aniline. And let's assume that we have a maybe ortho attack. So this is the intermediate that we'll be getting. Here there'll be a positive charge if you look at the mechanism. And here you will have a double bond. And here you'll have double bond. Okay, so what we'll be getting here? Let's rotate the electrons. So there is a possibility that will come here. And you'll be forming this compound. Okay, and next one, there'll be possibility that this will come here, and therefore the positive charge will be formed there. So, and then there's also possibility that this bond here will be formed. Okay, now this is in relation to the ortho, and the para is exactly the same thing, so I'll not repeat it again. So let's do the meta. Let's assume there had been a substitution in the meta position. Okay, so as a result, this bond can move in here. Can be getting this. And also, there is possibility that this bond will move in here. Excuse my drawing. Fine. And basically that's it. Okay, so what is the observation here? What can we notice? Well, we can notice the following, that in case of the ortho, and as I said, the bar will have these four resonance structure, whereas in case of meta will only have three. So what is the difference between the two? As you can see here, when we had the electron donating group, one of these structures had a direct contact, a direct sort of uh, approximation with the uh, with the or direct interaction with the electrons, which highly stabilize this shape here. Whereas in case of the meta substitution, we didn't get any we didn't get any shade, any resonance structure where there is a direct stabilization of the carbocation with the electrons. And therefore, the summation of these structures will give more stability than these ones. And therefore, the direction when you use the electron withdrawing or electron donating groups will be uh, towards the ortho and towards the para. Because as I said, if you draw the para, you will be getting the same result. You will get one of the structures having a concentrated electron density on it, which will enhance its stability, and therefore it will enhance the outcome from this route of the reaction as compared to this one. Okay, now let's look at what will happen if we use electron withdrawing group. Okay, so in this case, we can use the acetophenone as an example. And one time, maybe we will put the substituent group in the para position, in the ortho position. So we will call it maybe Y or E. And another time, because ortho and para, they will give the same structures. We will put it in the meta position. Okay. So in this case, there is a possibility that the bond, this bond will move here. Um, there is also possibility that this bond will move in here. And there is possibility that so these are the possibilities. Fine, fine. Now for this one, also there is a structure that we can similarly draw, which is this one. That's basically this. So this and this are equivalent. Okay, so what happens in this case, or what's the main observation? The main observation from this that when we put the subsequent group here in position ortho or para, in one of the shapes that you'll be getting, you will be getting a positive charge that's adjacent to the electron withdrawing group. And what the electron withdrawing group will do, it will destabilize the carbocation here. And because the carbocation is destabilized, this reaction route will not be favorable in relation to directing the incoming group, which we called it Y in this case, towards the ortho or the para. And this is the reason as why the presence of this shape here or this structure is highly unstable. Okay, now if we move on to the second one, and the second one is basically the substitution when it happens at the position of matter. I'll draw the shape. Let's call it A, H. Okay, so let's draw the possible structures here. To start with, there is probability that this one will form a bond here, and this will break into that direction. There is another probability that, in first place, there is another probability that we can draw here that instead of this going upward, maybe it can also go into this direction. And similarly, there is probability here that the electrons can move into that direction. What other probabilities we have? Basically, if this, um, basically these are the probabilities that we may encounter. Okay, so what can we understand from all this? Now let's take the observation. Now we have created a positive charge here I've created a positive charge in the ortho, we have created a positive charge in the ortho, and we have created a positive charge in the para. So what does that mean? It essentially means that the incoming group, it will not prefer to go into these positions because these positions are highly positive. So what does it mean? Because these positions are highly positive, the incoming group is positive. So basically they'll be repelling each other. And therefore because uh, the meta position is more electronegative than or have more electron density than these positions, the incoming group will prefer to go into that position, which is meta, as compared to the ortho and para. I hope this clear. This to clarify the orientation issue. As I said in the previous video, mechanism itself and these drawings are not uh, required from you, but this is only to clarify the meaning of the orientation and why it happens that way. Thank you very much.